Okay, this video has to do with the common ion effect. And so anyway, the first problem is just a basic Ksp problem. That's not the common ion effect. And then the second one down here is kind of almost the same problem, but it's showing the common ion effect. Okay, so anyway, here we go, the first one. So the Ksp. So we want to calculate the molar solubility. Basically what that means is if you make a saturated solution, that means you're dissolving the maximum amount at 25 degrees Celsius. How many moles of AgBr could you dissolve, or what molarity could you make it? Not how many moles, but what molarity could you make it a saturated solution of AgBr? So the first thing is you got to know how AgBr dissolves. And so AgBr would dissolve if you have a solid. You put it in water, and it's going to make silver ions and bromide ions. Okay, our equation is already balanced. It's a 1-to-1. Okay, so what we want to do is we want to make an ice table. And so remember, with an ice table, initial concentration equilibrium. Okay, solids don't matter because they're not part of the equilibrium expression. So if we're doing this in pure water, there's no silver and there's no bromide in pure water. But as it dissolves, the silver is going to go up by plus X. The bromine is going to go up by plus X also. So at equilibrium we have X and X. Now, the next thing is we'll write our Ksp for silver bromide. So Ksp is going to equal the Ag concentration times the bromide concentration at equilibrium. Then we plug in our number. 5.4 e to the negative 13 is going to equal X for silver and X for bromide. And so we basically get 5.4 e to the negative 13 is equal to X squared. And if we solve for X, we end up getting 7.3 e to the negative 7 molar. So that would be the molar solubility of silver bromide in pure water. Okay, you could make a solution of silver bromide 7.3 e to the minus 7 molar. That's the maximum molarity that you could make it. Okay, now let's look at this one. Basically, it says calculate the molar solubility of silver bromide in 0.5 molar silver nitrate. So already in your solution, instead of just having pure water, already in the solution there are silver ions and nitrate ions because it's a silver nitrate solution. All right, so keep that in mind. But anyway, the first thing you do is just write down, like we did in the problem above, like how silver bromide dissolves. And so it's going to be Ag plus 1 plus bromide negative 1. These are AQ when they dissolve in water. All right, so we make our ice table, initial change equilibrium. Okay, so solids don't matter. Okay, now here's the trick to this common ion effect. Instead of starting off with 0 silver, there's already some silver bromide in there. And so you're already starting off with 0.050 molar of silver bromide. So that's 0.050, okay, of silver nitrate, but there's already that much silver. Now there's no bromide in here, so that is 0. Okay, so this is going to go up by X. This is going to go up by X. So at equilibrium, we have 0.050 plus X. And here we just have X. Okay, next we'll write our Ksp expression just like we did up above. So it's the silver, and it's supposed to be plus 1, not 7, and the bromide. All right, then we're going to plug in our number, so 5.4 e to the negative 13 is going to equal silver, which is 0.050 plus x times the bromide, which is x. Now, one problem that you might notice if we did this math is we're going to end up with a quadratic. But because this number, this e to the minus 13, is very, very small, that means there's going to be not very much of this is actually going to be formed over here. It's going to be a very small number. So what that means is if you take 0.050 plus this x, which x is going to be very small, that it's not really going to change from this number. So what we can do is we can drop this x right here. And so if we just drop that x, we get 5.4 e to the negative 13 is going to be equal to 0.050, and we're going to multiply it times this x over here. And if we divide both sides by 0.050, we end up getting that x equals 1.1 e to the negative 11. All right, now that is the molar solubility in 0.050 silver nitrate. Now notice how that number is smaller than the number that we up here in pure water. Okay, you can dissolve more in pure water than you can in silver nitrate because basically silver is already taking up some space in between the water molecules. That's why you can dissolve less. And if you took 0.050, just let me show you about dropping the x, 0.050 subtract 1.1 e to the minus 11, well, that's going to be 1, 1, well, wait a minute, 0, 0, 0, 0, 0. I got to go all the way out like 11 spots. I don't know how many, 1, 2, 3. Well, whatever, you get the drift, but when you add those to it, that's adding, by the way, that's still going to be 0.050. That's why we could drop the x. It's not really going to make any difference. Okay? So remember that on these common ion ones, when it looks like you're going to have to do the quadratic, in AP chemistry anyway, most of the time you're going to be able to drop the x. All right? Okay, so why don't you try this one on your own and see if you can do it. So pause the video and see if you can do it. All right, so here's how you would do this one. So nickel carbonate. So you would write the dissociation or dissolution equation for nickel carbonate, nickel 2 carbonate. So it's going to be nickel plus 2 plus carbonate minus 2. All right, then you make your ice table. And solids don't matter. Okay, now it's in a 0.0020 of nickel nitrate. So we look for a common ion, and the common ion is nickel. Okay, the nitrate is not a common ion. See how the nitrate doesn't match nickel carbonate? So the nitrate doesn't matter, but the nickel does. And so that's going to be 0.0020 is how much you start with. The carbonate is 0 because there's no carbonate, okay, in the solution that you're going to start with. So this is going to go up by x. This is going to go up by x. And so at equilibrium, you're going to have 0.0020 plus x. And here you're just going to have x. Then we write our Ksp expression. Ksp equals nickel plus 2 times carbonate. Oops, I forgot the C. CO3 minus 2. Okay, and then we're going to plug in our numbers. So 1.40 e to the minus 11 is going to equal this 0.0020 plus x times x. Now, once again, this number, this Ksp is such a small number, which means very, very little of this is actually going to dissolve. And so what you can do is you can just drop the x. And so then you're going to get 1.40 e to the negative 11 is going to be equal to 0.0020 times x. And so if you divide both sides by 0.0020, divide both sides by 0.0020, you end up getting that x is equal to, let's see, I guess this only has 2 significant digits, so basically I think it rounds out to 7.0 e to the negative 9. And then you can just see, well, hey, did x really matter? If you add 7.0 e to the negative 9 and you add that to 0.0020, you still get 0.0020. So it's okay to drop that x. Okay, so that's the molar solubility of nickel 2 carbonate in a solution of nickel 2 nitrate. Okay, one more problem. Try this one on your own and see how you do. Okay, here's the solution to this one. So what would be the solubility of calcium fluoride? So calcium fluoride solid. Okay, it's going to break into calcium ions plus 2 fluoride ions in solution. Okay, make sure you balance the equation correctly. Okay, we'll make our ice table. Initial change equilibrium. Okay, solids don't matter. Okay, so now we're starting off already in a 0.200 molar solution of calcium nitrate. Calcium is the common ion. Okay, fluoride's not common, so that's 0. Okay, this is going to go up by x. This is going to go up by 2x. Remember, 2x. Okay, so at equilibrium, we have 0.200 plus x, and here we have 2x. We write our Ksp, and our Ksp is equal to calcium 2 plus times fluoride negative 1 to the second power. Okay, notice I didn't put 2f. Okay, we take care of that here in the ice table. The square though goes there. Okay, so then we put this in 5.30 e to the negative 9 is going to equal 0.200 plus x times 2x here squared. All right. Now, anyway, once again, the number is pretty small, and so we can drop the x, so we'll just get rid of that. So then we're going to have 0.530 e to the negative 9 is equal to 0.200. And I'm just going to do the math. 2 squared is 4, and x squared is x squared. So that gives me 4x squared. Okay, then if I do the math and I solve for all this here, I'm going to get, let's see, if I get that x is equal to 8.14 e to the negative 5. Okay, so that would be the molar solubility of calcium fluoride in a 0.2 molar solution of calcium nitrate. And you could see if you took 0.200 and you add that to 8.14 e to the minus 5, you're still going to get 0.200. All right, so that's it for the common ion effect. Email me if you have any questions.